Okay, so lead code 106, construct binary tree from Inorder and Postorder Traversal. So you're given two integer arrays, Inorder and Postorder, where Inorder is the Inorder traversal of a binary tree and Postorder is the Postorder traversal of the same tree. So construct and return the binary tree. Well, the reason why we're given two arrays is because with a Postorder you cannot create the binary tree. You need an Inorder traversal to help you determine. So the way we do this is Postorder, with Postorder, right? The root at every level is going to be at the end, right? As you can see here, 3 is over here, 20 is over here, 7 is over here, 15 is over here, and then 9, which is over here. Because Postorder is left, right, root. Right? So it will be the last one, but unlike in the pre-order where we just were able to just shift forward, we need to pop it off. Right? And you're going to see why. So once we get the root here, which is 3 at the end, we find it in our Inorder traversal, and we get that index and use it to determine which portions we're going to divide the rest of this, right? So if you've seen the solution for pre-order, then this should be easy. So first thing we need to do is we identify if one of them is none, then we return none at this level, right? So if Inorder, if not Inorder or not Postorder, then we return none, right? Otherwise, we find the root val, which for Postorder will be at the end, right? So we say root val is equal to Postorder dot pop, right? So why do we pop instead of doing Postorder? The reason we pop is to make it easier for us to construct the left and right, because once we pop this off, we just remain with an array from this portion to this portion, right? I guess we could have figured out a way of doing it, but this is one of the simpler ways. You just pop it off and then you just remain with this for when you're doing the left and the right. So now that we have that, we find this root val's index in the Inorder traversal, so we know how to split the remaining parts of the Postorder, right? So we'll call it mid is equal to Inorder.index root val. So again, remember what this code does is it searches through here and finds so our root was 3, so it comes, looks here, and it sees, oh, 3 is at this position, and returns this index into mid. And now we know that for the Postorder, this, when we're doing the recursive call, this will be the right side, this will be the left side. So when we come here, this will be the left side, this will be the right side. So we create our root node, right? We create our root node. So root is equal to tree node, val is equal to root val. We could have put this even here, like before here. So now we can create our, actually we should have put this here. It makes more sense to create that. So now we can create our recursive call to build the left and right nodes, right? So root.left is equal to self.build tree Inorder preorder, right? And then root.right is equal to self.build tree preorder Inorder. Oh shit, did I mix them up? Yeah, I mixed them up. Sorry. Okay. Right, because here this is how they're arranged. So for the Inorder, we're trying to, since our root at this level was 3, right? What we're trying to return for the Inorder, on the left side is this part, and on the right side it's this part. So on the left side, we want to get everything from the start until mid, right? We want to skip this, so we're doing mid, right? And then for the preorder, we want to get this part, right? So that means we'll be doing everything up until the mid as well, right? Did I say preorder? It's supposed to be postorder, sorry. Postorder. Postorder. Right? Because we want to get everything up until the mid. We want to include the mid. Right? So for Inorder again, we want this part. Right? So we start from mid plus 1 onwards. Right? So mid plus 1 onwards. And then for postorder, we want this part. So it will be from mid onwards, right? Because we want to get this part, right? And it will be here. But remember, since we popped off, right? Since we popped off, it will be, we'll only be dealing with this section. So we want to get this part, right? So after that, we simply return our root. And this should work. Voila. So this is the tricky part here. Actually, I would suggest what you do in an interview. You should type out a sample input, if there's any. You could ask for a sample input to help you visualize how to construct this out, right? So yeah, that's the solution to this. This takes O of n time and O of n space, but it's a bit inefficient in terms of the space because you recreate small arrays, right? So this makes it a bit inefficient. But yeah, that's the solution. And yeah, so thank you and bye.